Hi, welcome to Describing Chemical Equations, also known as Balancing Chemical Equations. This is where we're going to take what we can have here with a formula equation without the coefficient and balance it to making sure that we actually have the correct relationship of molecules to molecules. So, when we have a chemical reaction, we have a couple things in mind. Chemical equation describes a chemical reaction using chemical formulas and symbols rather than words, rather than pictures. It's just a way of using symbols. This is what makes chemistry sometimes challenging, is due to its high amount of symbols that we use. Now there's 7 diatomic molecules. They make a little 7 and point at the 7th one because of the fact that in its elemental form they're not found as atoms, they're found as molecules. Molecules are non-metal compounds that are bonded together. You need to know those, so memorize them, put them on your note card. You need to have them when you're doing these. Now there's some possible signs of a chemical reaction, and we've seen some already in class. Evolution of heat and or light, production of gases like bubbles, forming a precipitate, a solid, so you see the little powder that's formed from when we mixed the dropper bottles and we saw color changes with chunkies in it. And of course, regular color change without that as well. You notice this when an apple goes rotten. So these are the different signs of a chemical reaction. You see them, we've used them. So different ways to represent the same thing. They have to have a couple of things in order to be a chemical equation, meaning correct. Correct chemical formulas. Law of conservation of mass is where we use for the coefficients, because the idea is that if we start off with 1 methane molecule and 2 oxygen molecules, we get all the same atoms, which means no atoms are destroyed, none are lost. They're all contained within the chemical reaction. The bonding does change, but not in any pattern. These are all single bonded. These are double bonded. Now this carbon has double bonded oxygens and single bonded oxygen to hydrogen. So it does change. We'll explore that a little bit later when we talk about energies. But it does change, but we don't have any particular pattern for that, so we're not going to use patterns to explore how these are going to be made. So when it comes to some little vocab, we have a formula equation. That is an equation of the chemical formulas. What you can see is no coefficients. So we often provide you the formula equation, and when you're making your own formula equation in the next lesson, then you need to balancing it, making a chemical equation. So a formula equation is a chemical reaction made up of chemical formulas. A chemical equation is a formula equation that is balanced in order to satisfy the law of conservation of mass. So that's why we can't use this just as is. We can't use it for quantitative relationships because it's not necessarily a 1-to-1 ratio. So we need to make sure it's balanced in order for us to use it. You've seen some of these symbols before. Just keep in mind, if you see them, don't be scared of them. They're just trying to tell you the states of matter, again, giving us an idea of the chemical reaction. So let's just take a look at balancing one of these. I'll go into a little more rules and stuff, but I just wanted to give you an idea of what this kind of looks like. So you've got 1 barium. Oops, I need to be able to draw. 1 barium, 1 barium, 2 chlorines. I've only got 1 chlorine, so I'll need to use a coefficient in front in order to make that 2. I've got 1 silver on this side, 2 silvers on this side, so 2 needs to go here in order to get 2 silvers. You want to keep your polyatomics all together. So 2 nitrates, because NO3, if I were to kind of highlight it here, NO3 is 1 polyatomic ion. You don't separate it. You got to know what those are available. You don't need to memorize them. You need to be able to identify them. And then I've got 2 nitrates over here. So this is now balanced. And this would be my chemical equation. So I changed a formula equation into a chemical equation. Now, what are they used for? What can they be used for? So we can do relative amounts of reactants and products. This is what we call stoichiometry. We'll do that next unit. Relative masses can be determined from the chemical equation. That's also helpful because we'll talk about that also with stoichiometry, being able to use their chemical formulas to determine how heavy these things are. The reverse reaction equals the forward reaction. So likewise, if we were to start off with this stuff, and it would react to make this stuff. So the idea is that the same thing going forward is the same thing going backwards. That's very helpful. Now, what are they not an indicator for? What can they not tell us about if it will occur? Just because you can write it and balance it and it's all good doesn't mean it will actually happen. There's other factors to see if something will react or not. It may not exist, meaning that at this stage, it might need to be at a higher temperature to react. This may be there is no condition in the universe in which it's going to react with those two reactants. The speed, we don't know if this would take hours, minutes, seconds, days, or any length of time. And then it doesn't show anything about bonding, about if they're double bonds, single bonds, ionic bonds, all this other kind of stuff. So that is what it's not used for. Now, a quick how-to. I'll just kind of go through these, but you want to write these down so you have these for your disposal as you balance equations. All right, so it says get the formula equation, but that'll be really provided essentially because we used to start off with just the words, the names, and students needed to translate those into the formulas. Now, here's one that's a kind of a trick that, or technique, I don't like the term trick, technique I picked up, is that if you have hydroxide present in a compound, change water, if present, to HOH. This enables you to see the OH. Oops. This enables you to see the OH and be able to bond it easily, not bond it, balance it easily when you have OH in the compound. It really works a lot better when students are struggling with ones like those. I show them that technique and boom, now it's like it was easier than it ever was before. Polyatomic ions, keep them whole if it doesn't split up. This is really rare. We generally provide you ones that polyatomics remain whole. Balance things that appear only once on both sides of the equation. So if you only have sodium in one place on the left side of the arrow, one place on the right side of the arrow, we want to make sure that we balance those first, rather than if we have oxygen in two spots or carbon in two spots. That makes it more challenging to do. Do one element at a time, like you saw me do back here, to where I did one element. I kind of worked my way towards the arrow, did barium, then chlorine, then and I worked my way towards the arrow. That's going to make it organized for yourself so you don't miss anything and circle back. Free elements, so elements that are by themselves, they're not bonded to any other different elements. Leave those at the end, because when you add a coefficient to those, all that happens is the fact that that one will change, and that's usually what you're trying to change last. Start with the first compound, work its way towards the arrow. You might need to backtrack, but it's rare that will be occurring. All right, so let's put these into action. So I'm going to just start off, I'll go blue with this one. I got one sodium, one chlorine, two chlorines. So I need to get two here in order to get my two chlorines. Don't worry about the sodiums. Just leave it as is, go on to the next element. One barium, two nitrates. So I need two nitrates here. So I'll need a 2 to go here. Now this will give me two sodiums, in which, hey, look at that, I've already got two sodiums, balanced. This one is an example of a combustion reaction. I've got two carbons, only one here. So 2 will need to go here for the carbon. Two hydrogen, okay. I've got two oxygen, and I've got 2 times 2, which is 4 oxygen, and 1 oxygen here, for a total of 5. So you might notice, I have 5 on the right and 2 on the other side. That's going to become problematic. Well, there's a simple fix to this. When you run into this problem of an odd number of oxygens in a combustion reaction to an even number, of course our oxygen, you can always just make any odd number into an even number by multiplying it times 2. So you can see my coefficients in blue. I'm going to double everything that's there. So the 1 that's in C2H2 becomes 2. The 2 becomes 4. The 1 for H2O becomes 2. Now I haven't done anything for oxygen yet because I didn't have one for that yet. Now let's just go back and double check my numbers. So for carbon, I've got 4. For hydrogen, I've got 4. When I come over to the left side, for carbon, I now have 4. Oxygen, I now have 8. Hydrogen, I now have 4. Oxygen, for that one, I have 2, for a total of, no surprise there, 10. So now, in order to get 10 for the oxygen, a coefficient of 5 will work. This is, you can tell, is correct because you cannot reduce any of these by the same number. The coefficients in front always need to be the lowest ratio. So 2, 5, 4, 2, that can't be reduced because you can't divide 5 by an even number. All right, let's look at the next one. So I have a free element to start, calcium. I'm going to leave that so far. Now I've got sodium. I've got 2. It's a free element as well, so this might be the only time I'm doing it. So 2 sodiums. I've got 1 sulfate, 1 sulfate. And I can see I've got 1 calcium here, 1 calcium here, so I'm balanced there. Looks like I forgot the little line for sodium there. So now I'm balanced. Now the last one, I've got OH present, and I have water present. So I'm just going to walk it through and see why it's a good reason to change this to HOH. Give you a heads up. It's a little black. So I've got 1 aluminum, 2 aluminums. So I need to make this a 2 to give myself 2 aluminums. Now 2 times 3 hydroxide is 6 hydroxide. Now I look over to the right side and I go, where's hydroxide? I got an H, I got O, I had the 2 to 1. What's going on? But watch what happens when I change this to H, OH. So it's 2 ions almost as if together. So 6 hydroxide, I currently have 1 hydroxide. 1. So in order to get 6, I need a 6 coefficient. So now I have 6 hydroxide, 6 hydroxide. I have 2 hydrogen. I now have 6 hydrogen because again, 6 times the 1 hydrogen. This is not hydrogen, this is hydroxide. 6 times 1 is 6. So I need to have a 3 in front to get 6 hydrogen. 3 sulfates, and now I'm balanced. You can clearly see when you change HCO to HOH, it makes it much more visible. Many of us are visible learners, and humans are made to see things. So that's why it's important that we write things best for ourselves so we can understand how to do this. We're going to get lots of practice, so come in with any questions. See you soon.